Okay, hyvää iltapäivää. Sorry, I'm a little bit late. Do you hear my voice now? We have considered these first things some weeks ago. We had started this vectors and matrices course, and then we had these some concepts there, vector scalar quantities and vector quantities. I'm sorry about the quality of this camera. There is some mistakes there. I don't know why does it show so nasty like right now. And we calculated some cases there, created vectors with the help of coordinates, and calculated the lengths of the vectors, and unit vector we had there, and then also some rules, addition and subtraction rules there, and multiplication rule and scalar product or dot product. And then one application when we had a triangle and we wanted to calculate the angles of that triangle, and we used the dot product there. And I think this is a thing which you have had those assignments that you have those first 4 assignments handle these things, simple calculation rules and the dot product, and using dot product when you calculate the angles between vectors or the angles in triangle. And then I will continue. So let's take here force vector. I'm really sorry about this quality. This is not at all a good picture, but I hope you can understand what I am writing. So let's take example. We have a force which has magnitude of, let's say, 23 kilonewtons or 23,000 newtons. Has a direction of vector AB, where this A has coordinates 5, 3, 7. The unit of these coordinates are meters, and B has coordinates -1, 2, and let's say take 10. For example, this kind of situation. And well, I will change a little bit. I will put minus sign in front of this number 3 there, and we know the magnitude of this force, 23 kilonewtons, and then we know the direction of that force. It has the same direction as this vector AB, and we know the coordinate values of those points A and B. And let's form a force vector. And in this case we we have to do this with some steps. The first step would be the formulation of the vector AB. So let's take step 1, vector AB. So AB starts from point A and it ends to point B, and the vector AB we get when we, I will use this bracket form of the vector. The vector expression of this vector, coordinate expression of this vector AB will be we get when we subtract the coordinate values in that order that we start from the point B. So we take coordinates from the B, and we in the first place here in the coordinate form of this vector. So these values there are the coordinates of the point B, and then we take minus sign and we subtract the values from the vector from the point A. So we take these values here 5, and here this is a reason I take this sign minus there, because there we get 2 minus signs. This is mostly when students and when I do these calculations, mostly those errors comes when you have negative coordinate values. So we have to remember that we have the minus sign, and then we have this sign, which is the sign of that coordinate, y coordinate of the point point A, and then 10 minus 7. So we just first coordinates of B, and then coordinates of A in that order. So we get minus 6, and here we get 2 plus 3, it will be 5, and then 3. In those assignments which I have checked at this point, I think most errors in these vector calculations, there has been these sign errors there. It is very easy thing, but mistakes are always possible. And the next one will be to find the length or magnitude of this. One thing, we have these coordinates m here, so I will use coordinates also here. I write this meter to the end of that vector, but of course I could use also that meters inside of that bracket form there, but it is easier to put that the unit at the end, to the end of that vector. The length or magnitude of this vector, because now it is actually meters, so it is very easy to use the word length there, but also it is, we can call it the magnitude of AB. So we will get this AB, the length of the AB, by using these lines here, which we use mostly in absolute value, but also in vector lengths or magnitudes we use these lines there. But of course I could also use simple notation AB without any lines above it or any lines around it, and then I will get this with the help of, I will use those brackets there. Of course they are not necessarily when you have positive numbers, but with the negative number you always need to use the brackets, or just drop the negative sign away. But if you are using that negative sign there, then you need to have these brackets there. because if you leave those brackets away, then you will get the wrong answer. So can I do this without calculator? Probably not. 45 plus 60, 70, square root of 70. And in this case, I don't think it is necessary to get any decimal value of this, because we don't actually need that decimal value. It is more easy to use this square root there. And then step 3, we will create a unit vector which has a direction of AB. This unit vector, I think people probably remember from those lessons some weeks ago. First I had this example there. I first forgot to use this notation there, but then I added that later here. So in those lessons we did not write these things, but it is now there added. So this unit vector, we use this form that we get the exponent 0 there to express that we are having a unit vector, or the vector which has the same direction as the original vector, but the length of the vector is simple 1. Here also I am forgetting all the time the units there. This length of this vector actually is meters right now, because the units were the meters. So now we are forming unit vector in the direction of AB, vector AB. So these steps we need actually all the time when we are using vectors which are or forces which act on third dimension or 3D space, and right now we are having three-dimensional space, so we need to use these things here. When we have a plane problem or vector which has only which act only in plane, for example XY plane, then we don't need this kind of hard process when creating those vector formations. It is very easy when we have two-dimensional case, and we will take an example after this when we have two-dimensional case. So this unit vector which has the direction of AB, we get by dividing this AB vector by the length of that vector. So here we had this AB vector, and here we have this length of that vector. So we are having -6, 5 and 3 meters and square root of 70 meters. And as you see, when I use these units right now in this example, we notice that there are meters in the top part and also in bottom part of this division, so we can cancel them away. So this unit vector actually even though its name is unit, it actually don't have any units there or physical units. This unit doesn't mean the same in this case. It means only that the length of that vector is 1 unit or simple 1. So in this case we just divide every coordinates here with this same number, square root of 70. So we get this kind of unit vector. And this hasn't any physical units anymore. It is only simple. These are only simple numbers there. And then the hardest one is over. We have 3 steps, and now we know the unit vector which has the direction of AB, and the 4th step is that we are having this magnitude here, and we are having this unit vector, and when we multiply this magnitude with this unit vector we get the force vector. So this step 4 sorry, did someone ask something? Probably not. Step 4, this force vector, and I will use this kind of notation many times. Force, we use the uppercase F letter, and when it is for vector, we use this vector line here, or that vector arrow. I usually mostly use this simple line there, and because this is a force vector which has a direction of AB, I will write AB here, some kind of subtrick there. And this we will get by multiplying the magnitude of this vector by the unit vector of this in this direction AB. So the magnitude of this vector, we will notate that with this absolute value sign, and then we multiply it. This is simple multiplication. It is not any dot product, because this dot product we had last time, or when it was this dot product was a multiplication between 2 vectors. For example, dot product A dot B, we have to use A is a vector and B is a vector, and we made that dot product with the help of those vectors. But in this case we don't. This is not a simple multiplication sign there, and this we will only multiply this. Sorry, not this kind of. We are having the unit vector AB. Sorry about this. This is only multiplication. So right now the magnitude of this force AB was 23 kilonewtons, and then we have this unit vector, and now I use this bracket form as I was already trying to do there, a little bit too early. So this will be the force vector. And really, when we are calculating with forces which act on three-dimensional space, then we need to use this kind of things every time we are calculating with those force vectors. This is not a very nice thing, but actually is not any easier methods, in my opinion. So then we may multiply these 23 times these coordinates here, and we will get the coordinate values there, and I will use that. So I will make this multiplication. I will take the decimal values after that I have written this exact form there, but the decimal value tells us more about that force. We can understand better what does that mean actually, this force vector. I will add the unit in the end of this vector, so I'm not forgetting that kilonewton there, but I will just add it in the end of this vector. So I just simply multiply every components of that vector with this 23. And this will have unit kilonewton. Let's take this. As you see, I have solved some equation with this calculator. Actually, this is from a business mathematics course. There is some interest calculations there, but that does not have anything to do with this course we are having right now. Sorry about quality of this. This is the number we get from the first component. And then the next one. And the last one. Oh, sorry, kilonewton in the end of that. So we got this kind of vector, force vector, minus 16, approximately minus 16, and approximately plus 14, and then approximately plus 8. So this means that the first component here tells us the force in the direction of x-axis. I will try to find better. Force component in the direction of x-axis, and I know I'm not going to write almost the same sentence here. Here we have also the same as this is the force component in the direction of y-axis, and the last one is the force component in the direction of z-axis. If I try to draw this force vector, that would be, I hope I find some. So I will try to draw a three-dimensional picture of this case. So x-axis is coming to me or to the direction where I sit here, and the y-coordinate will go to the right and z-coordinate to the up. This is so-called right-hand rule or right-hand coordinate system, which means that when we are having these three fingers, which I don't remember the names of English, thumb is this index finger. Do you know better English than me? This finger, and then the middle finger. in Finnish peukalo, etusormi, keskisormi. What does that mean? That this right hand system means that when I turn this page how do I this, my thumb is pointing in the direction of x coordinate, x-axis, and my index finger is pointing to the direction of y axis, and then the last finger, or the middle finger, will point to the direction of positive z-axis. So this is right hand system. This is my right hand here. So when we are having this force vector here, so we have the coordinate values here -16, so this will be the positive x-axis, so the negative x-axis goes to the opposite direction, so it goes somewhere here. And I will just let's say, for example, this is the place where the x coordinate is -16.4, etc. Oh, it is so small. And then first we go to the negative value of 16 in the direction of x-axis. Then we take about approximately 13.7 units to the direction of y coordinate, so or y axis. So we will end up first there. Then I will go to the direction of y-axis. This is 13.7, the length of that vector. And then we have the third component, which is the z component, and it has the value 8. So we go to the direction of positive z-axis 8 units, and let's say it is about this length. As I earlier said, so this is 8.24. So as I probably earlier said, that these three-dimensional pictures are very hard to write, and even though when we draw, and even when we, oh sorry, I have to accept one student. Sorry about. So this is very hard to draw, and even though if we draw this picture, we actually don't get a very good view of that actual vector, but we can see something. So this vector, the direction of this force vector is the direction of this. This will be the force vector AB. So we can think that there is some kind of wall in this YZ plane. There is wall there, and that vector points to the other side of that wall. If that wall is there, we can't see that vector there. So it goes in that direction, and then it goes to the right, and then it goes to up. So the approximately direction of that force vector is that blue vector there. But this is probably the only picture I am drawing in or trying to draw in third dimension, because these pictures actually don't tell us anything. But this is a force component, and if we have other forces also, which has a different direction or orientation in the 3D space, then we would do the same process with them. And if we, for example, have to add those vectors, then we simply add those components there. And for example, if we had force vector, for example BC, and we had to add it with the vector AB, force vector AB, then we just add those components, and that will be the resultant force or the sum force of these component forces there. Let's check if we calculated this correctly. If we I will call it step 5. This actually, it's not a very we can't be 100% sure if this code if it is went correctly, but if this checking doesn't work, we will be sure that we have made some mistake. But even though this checking goes okay, then there is a small probability that we still have made errors, because we possibly could have made errors with these signs. That error may have come here. We may probably would have false signs in those coordinate values there, or component values there, and even though we had false signs there, we could get the same length of that vector, and we could get the almost correct unit vector. We just had different signs there, and when we are calculating the force vector, we will simply multiply that magnitude of that force with the unit vector, and again we may have different signs there, and even though we had totally different signs here, we would get the length of that vector or the magnitude of that vector correct. But still, it is possible. It is useful to do this checking, because if we have made a mistake, we probably can see that. I will call it checking by calculating the magnitude of this vector. And we will do that by using the Pythagoras. So we just take these components and we raise those to the power of 2, and then add them and take square root. So we will get I will simply use those decimals which I have written in the paper. I have those exact ones in the calculator, but I will use only these values, and this will be kilonewtons. Let's do that. Of course, we know that this will, sorry, not this. Of course, we may be quite sure that this went correctly, but let's see. So I will take the square root, and I will show this just to show that if we are using those rounded values there, then we will not get exactly the correct answer, but we can see that it will be almost correct. So this is, as you see in the screen, those values there you can see still those exact values you can still see in the screen, but I have used only first decimals there, and then if I check this, I will get this kind of value, 22 point, how many nines there are, 4 nines, 27, etc. kilonewton. So if I check those rounded values I used there, sorry, I all the time look at the wrong camera. Every time this camera in this studio is in the wrong place in my opinion, but I always now I am watching the camera. I used here rounded values. Here I have 6 numbers, here I have 7, and here I have only 5 numbers there. So the most inaccurate value there is this bit, which has only 5 numbers, and that gives us some kind of certainty of the 4 first numbers of the result. Here is 5 numbers, 7, 6. The most inaccurate is 5 numbers, and the result we can be sure of the first 4 numbers. So there we can see first 4 numbers, and if we round this value in the with the precision of 4 numbers, and we see the first decimal there is 9, so this will round up to value 23.00. So this will be rounded 23.00 kilonewtons. And actually when we check the starting value there, we see that the force had actually the value magnitude of 23 kilonewtons, so probably we had made everything correctly. So this example tells us that actually this 3-dimensional vectors and 3-dimensional forces are very hard work when we are calculating with these. Of course, this is not very hard. This is quite simple mathematics. Only sum or subtractions there, and square root, Pythagoras theorem, then dividing by numbers there, and then here also multiplication. So it's just simple mathematics, but there are many steps there, and there are many places where you can make or I can make mistake. So this is our final result of this force vector. As I told, this 3-dimensional case is mostly they are long calculations. There are many steps to calculate, but luckily the two-dimensional case is much more easy. So let's take that kind of example next. Or sorry, let's have a small break here. I will let's have a break of 10 minutes. Continue. Fifteen in Finnish time. Actually it is right now 5:15. Okay, I will have a break. I will ask the question to the chat box there.